second lesson for the week, lesson 14. Make sure you have that in front of you, please. Modeling relationships with a line. We talked yesterday, or talked this in the last lesson, about ways to represent our data, whether it be with a quadratic function, a linear function, or an exponential function. All right? Let's go ahead and look at example number 1. It says, Kendra likes to watch crime scene investigation shows on television. She wanted to show where investigators used a shoe print to help identify a suspect in the case. She questioned how possible it was to predict someone's height. She questioned how possible it is to predict someone's height is from his shoe print. To investigate, she collected data on shoe length in inches and height in inches from 10 adult men. Her data appears in the table and scatter plot below. So she let x equal the shoe length and y be the height. Alright, so let's just kind of go ahead and answer a couple of questions about this. Is there a relationship between shoe length and height? Do we see a relationship between the height of men and their shoe length? Yes, it's not a strong relationship, but if we look, it looks to appear that as the men get taller, their shoe size appears to be bigger. All right, so it does look like that there is a relationship. How would you describe the relationship? All right, well, we just kind of talked about as the shoe length increases, the height of the men increases. I kind of went a little backwards, but as the shoe length increases, the height increases. Do the men with longer shoe lengths tend to be taller? Well, yes. I mean, longer shoe length, it looks to be that they do tend to be taller. So men with longer shoe lengths are taller, according to our data. All right. Example number 2. All right, let's look at example number 2. It says, when two variables, x and y, are linearly related, you can see a line to describe the relationship. You can also use the equation of the line to predict the value of the y variable based on the value of the x variable. For example, the line y is equal to 25 3/10 plus 3 66/100 x might be used to describe the relationship between shoe length and height, where x represents shoe length and y represents height. To predict the height of a man with a shoe length of 12, you would substitute 12 in for x in the equation of the line and then calculate the value of y. So you would get y is equal to 25 3/10 plus 3 66/100 x, which is 25 3/10 plus 3 66/100 times 12, which is 69 22/100. So you would predict the length or the height of 62 22/100 inches for a man with a shoe length of 12 inches. All right, I want to remind you that a model, an equation, can be used to describe the relationship between variables. All right? Models can be used to make predictions by substituting a value for one variable to solve for the other. All right? So, because I knew the height or the shoe length of the man, then I could predict his height. All right? exercise number 3. Below is a scatter plot of the data with two linear models. Y is equal to 130 minus 5x, and y is equal to 25 3/10 plus 3 66/100 x. Which of these two models does a better job at describing the shoe length and the height, and show how the shoe length and the height are related? Explain your choice. Well, here is the line for y is equal to 130 minus 5x. Here is the line for y is equal to 25 3/10 plus 3 66/100 x. Well, let's look at this. 1, when I draw a line, I want my points to be close to that line. 2, I want my line to show what my data is saying. Here, if I chose this line, 1, my points are pretty far away. 2, this is basically saying that as the shoe length increases, the height of the man decreases. Alright? And that is not what my data is saying. This line here fits better because it is closer to the majority of the points, and it represents the fact that as the shoe length increases, so does the height. So we're going to say the line y is equal to 25 3/10 plus 3 66/100 x is a better choice. Because it shows as the shoe length increases, so does the height. Alright? So we want to make sure our line is also showing what the data is showing. One of the men in the sample has a shoe length of 11 One of the men in the sample has a shoe length of 11 8/10 inches and a height of 71 inches. Circle the point in the scatter plot in question 3 that represents this man. Well, I'm looking for a shoe length of 11 8/10, so that's going to be close to this, and has a height of 71 inches. So let's see where they meet. This would be that point. Alright? That would be the point that we are looking at. Alright, number 5. Suppose that you do not know the man's height, but do know that his shoe length is 11 8/10 inches. If you use the model y is equal to 25 3/10 plus 366x, what would you predict his height to be? Alright, well, let's look at y is equal to 25 3/10 plus 3 66/100 x. So if I know his shoe length, alright, as 11 8/10, shoe length is represented by our x, so I would do 25 3/10 plus 3 66/100 times 11 8/10, alright, and when I plug all of that in, so the calculator, let's see, I get 25 3/10 plus 3 66/100 times 11 8/10, I get approximately 68.488. Alright, so we would say approximately 68 inches. Alright, now it says if you use the model y is equal to 130 minus 5x, what would you predict his height to be? we're going to do the same thing. Plug in 11 and 8/10 for our x, and I get 130 plus 5 times 11 and 8/10 gives me hang on, I plugged that in wrong. 130 minus 5 times 11 and 8/10 gives me 71. All right. Which model was closer to the actual height of 71 inches? Well, the model y is equal to 130 minus 5x is closer to the 71 inches. Is the model a better fit for the data? And explain your answer. But that is not a better model because this one here, y is equal to 25 and 3/10 plus 3 and 66 x is closer to more of the points. It is closer to more of the data points. So just because it worked for this one point does not mean it is the better fit line. All right, number 7. Is there a better way to decide which of the two lines provide a better description of a relationship rather than just comparing the predicted value to the actual value for one data point in the sample? All right, so here's what we need to understand. The better line, or the best fit line, is the one where the distance from the points to the line are as short as possible. So the better fit line is the one where the distance from the points to the line is as short as possible. All right? So I want it to be as short as possible. All right, example number 3. One way to think about how useful a line is for describing a relationship between two variables is to use the line to predict the y values for the points in scatterplot. These predicted values could then be compared to the actual y values. For example, the first data point in the table represents a man with a shoe length of 12 and 6/10 inches and a height of 74 inches. If you use the line y is equal to 25 and 3/10 plus 3 and 66/100 x to predict this man's height, you would get this. So plugging in 12 and 6/10, you would get 71 and 42/100. Because his actual height is 74 inches, you can calculate the prediction error by subtracting the predicted value from the actual value. This prediction error is called our residual. For the first data point, the residual is calculated as follows. The residual is equal to the actual y value minus the predicted y value. So 74 minus 71 and 42/100 is equal to 2 and 58/100 inches. For the line y is equal to 25 and 3/10 plus 3 and 66/100 x, calculate the missing values and add them to complete the table. Alright, so we've got our shoe length, we've got our height, we need to find the predicted value. The predicted value is where I plug, if you go back, the predicted value is where I plug my x or y in to my equation. Alright, so the first one's done for us. Alright, so the second one, I'm going to plug 11 8/10 in for x on my equation, and I get 68 49/100. The actual height was 65. So I would take the actual height and subtract the predicted value, which is why I get a -3 49/100. Alright, the next one is 12 2/10. Plug that in for x. When I do that, I get 69 95/100. So now I'm going to subtract 71 minus 69 95/100, and I get 1 5/100. Alright, this one's done for us, this one's done for us. Let's look at this one. They want us to find the residual. So 68 minus 67 2/200 is 98/100. This one's done for us. We need to plug in 12 2/10 into our calculator, into our equation for x. When I do that, I get 69 95/100. Alright, so you would see what that is. Alright, and the rest of them is done for us. Alright, why is the residual in the table's first row positive and the residual in the second row negative? Well, in the first row, the actual value is larger than the predicted value. The actual value is larger than the predicted value. In the second row, the actual value of 65 is less than or smaller than the predicted value. That is why I have the positive and negative residuals. Alright? What is the sum of the squared residuals for the line y is equal to 25 3/10 plus 3 66/100 x and the data of exercise 11? Alright, so it says the sum of the squared residuals. So I would square, alright, here's what I would do. Let me pick my calculator up. And we want to know the sum, so I would just put these in the calculator all at once. Give me just a second. The one thing you want to make sure you do is when you enter a negative number, I would suggest you put it in parentheses and then square it. Because if you don't, it will not square the negative part of your number. Alright? So make sure you're putting that in parentheses. Alright, so here's what my calculator looks like, so that you can kind of see what I've done. Alright, I've squared every one of the residuals and added them together. So it wants to know what is the sum. So I get let's see, what is the sum of the residuals? We're going to round it to the nearest hundredth. So 34 and 54 hundredths. Why did you get a number close to 0 for this sum? And does this mean that all the residuals are close to 0? Why did I get a number close to 0? Well, all of my squares are going to be positive. And when I add all of that together, guys, my residuals are not big. Alright, they are not big. Does that mean all residuals are going to be close to 0? Well, we're going to have to investigate to find that out. Alright? Alright, so let's look at it. Let's see here. What do we have? When you use a line to describe the relationship between two numerical variables, the best line is the line that makes the residuals as small as possible overall. If the residuals tend to be small, what does that say about the fit of the line to the data? Well, if my residuals are small, then that means that my line is a good line. That means that the distance between those points and that line it's very small distance. Alright? So if those residuals are small, then the points tend to be close to the line. Alright? Alright. Number 12. The most common choice for the best line is the line that makes the sum of the squared residuals as small as possible. Add a column to the right of the table in exercise 8 and calculate the square of each residual and place the answer in the column. Alright? So let's go through and we're going to do a square. And I'm going to let you guys do this. We're going to let this be part of your homework. And I want you to go through and square all of those residuals. Alright? Why do we use the sum of the squared residuals instead of just the sum of the residual without squaring? It says, hint, think about whether the sum of the residual of a line can be small even if the prediction errors are large. Can this happen for squared residuals? Well, if I just add up all the residuals, positive and negative residuals can affect one another. And you get a small sum even if some of the residuals are big. Alright? So positive and negatives will affect each other. And you would get a negative or a small sum no matter what. Alright? Alright. What is the sum of the squared residuals for the line y is equal to 25 3/10 plus 3 66/100 x and the data in exercise 11?
Pardon the interruption. Josh Pulaski to Miss Christie's room. Josh
We just
Pulaski
did
to Miss
that.
Christie's room. Thank you.
We just did that. The sum is 34 54/100. And I think, yeah, look, I messed up. I squared those here. I'm sorry, guys. I squared those. I misread the question. What is the sum of the residuals? If I add all of those up, I would get negative 6/10. Alright? I jumped ahead of myself. Forgive me for that. I make a mistake. Alright, but when I square them, I get the sum of 34 54/100. Alright? The line that has a smaller sum of squared residuals for this data set than any other line is called the least squares line. This line can also be called the best fit line or the line of best fit or regression line. So you've got 4 different names here, and you may see them named that all the time. For the shoe length and height data for the sample of 10 men, the line y is equal to 25 3/10 plus 3 66/100 x is the least squares line. No other line would have a smaller sum of squared residuals for this data set than this line. There are equations that can be used to calculate the value for the slope and the intercept of the least squares line, but these formulas require a lot of tedious calculations. Fortunately, a graphing calculator can be used to find the equation of a least squares line. It says your teacher will show you how to enter the data and obtain the equation of the least squares line using your graphing calculator or other statistics program. Okay, so I'm going to kind of show you this really quickly, and then hopefully it will work. So I'm going to go in and I need to enter all of my data. So it says enter the shoe length and height data, then use your calculator to find the equation for the equation of the least squares line. Alright, so I'm going to go back to my data here, and I'm going to let this be the shoe length. Alright, and then I'm going to come over here and I'm going to let this be height. I have a glare. Alright, then I'm just going to enter my data. So I'm going to do this very quickly so that way we don't take forever. Hopefully we can get back. If you have a graphing calculator, it may be a little different than what I'm doing. Every graphing calculator is different, but you can use the Desmos calculator online to find the regression line, or you could, like I said, if you've got one, that's fine. Alright, so here's what I'm going to do. I am now going to graph my data. As soon as I'm going to do a quick graph of my data. Alright, now, that's my shoe. Make sure I have my, okay, so here quick graph of my data. This is what my data looks like. So now I'm going to come over here and I'm going to ask it to give me my regression line. And you go to Analyze, Regression. I want it to be linear. Alright, so notice it put my regression line in there. And let's see what it says. It says y is equal to 25.2769 plus 3.6570x. So it wants to know, did we get 25 3/10 plus 3 66/100 x? If I round, then yes, I did get that. The exact equation is y is equal to 25.276859504133 plus 3.65702479338884x. Okay? But if I round to the nearest tenth, when rounded to the nearest tenth, I get y is equal to 25 3/10 plus 3 66/100 x. Rounded to the nearest tenth, rounded to the nearest hundredth, however, but I get that equation. Alright? Alright, number 15. Assuming that the 10 men in the sample are representatives of male adults in general, what height would you predict for a man whose shoe length is 12 and a half? What height would you predict for a man whose shoe length is 11 9/10? Well, predicted height of a man whose shoe length is 12 and a half. So I'm going to plug in to that equation. And when I do that, I get 71 55/100 inches. All right. The predicted height for a man with 11 9/10 inches, plugging that into the calculator, I would get 68 86/100 inches. All right, and all I did was plug that into our equation. Once you have found the equation of the least square lines, the value of the slope and the y-intercept of the line often reveals something interesting about the relationship you are modeling. The slope of the least square line is the change in the predicted value of the y variable associated with an increase of one of the values of the x variables. Give an interpretation of the slope of the least square line, y is equal to 25 3/10 plus 3 66/100 x, for predicting height from shoe size for adult men. Well, first of all, you need to recognize what the slope is. The slope is whatever is attached to the x. So my slope is 3 66/100. All right? All right. So what that means is for every 1 inch increase in a man's shoe length, so for every 1 inch increase in a man's shoe length, you would estimate an increase of 3 66/100 inches in height. So for every inch that the shoe length goes up, the height is going to go up about 3 66/100 inches. That's what the slope is telling us. The y-intercept of a line is the predicted value of y when x equals 0. When using a line as a model for the relationship between two numerical variables, it often does not make sense to interpret the y-intercept because an x value of 0 may not make any sense. Explain why it does not make sense to interpret the y-intercept of 25 3/10 as a predicted height for an adult male whose shoe length is 0. Well, since x represents the shoe length, it is impossible for shoe length to be 0 inches when a man is 25 3/10 inches tall. So since x represents shoe length, it is impossible to have a shoe length of 0 when a man is 25 3/10 inches tall. That would not make any sense. Alright guys, end of the lesson. Hope you've had a great week. Hope you have a great weekend. We are almost done, guys. Keep working hard, and I'll talk to you next week.